Thank you for having me. And I'm happy to be able to have the opportunity to present virtually. I'm going to talk maybe a little bit dovetailing off what we heard from Bob Fisher about stellar reacting flows, but I'm going to come at it from a slightly different perspective and focus mainly on some of the numerical challenges that arise and how that influences our understanding of turbulence. So just to summarize, and I'm sure you've seen all this already or will many times. When you model a star, you worry about hydrodynamics. So the stars are big. We can generate large convective regions. They're turbulent. There's a lot of mixing that takes place. We have combustion through nuclear reactions. That's the energy source of the star. Self-gravity holding the whole star together. Radiation and diffusion helping to transport the energy, and magnetic fields, as we just heard, which we love to ignore because things are tough enough. And when you model this whole system and you incorporate all of these pieces of physics, these multi-physics simulations become challenging because you have to respect the timescales that each of these different physics ingredients want to move at. And each of them has a different mathematical character. And so your solution method needs to take into account the preferred way for you to solve these. I'm going to focus on the problem of reacting flow. So I'm going to focus on the challenges imposed by modeling hydrodynamics and coupling it to reactions at the same time. And so just a little bit about some fun ways hydrodynamics and reactions can interact with each other. Turbulence and the burning that we have in the stars, they both affect each other. So burning can affect turbulence, and we heard a lot about this from Bob, that reactions can provide a dissipation scale that can be much larger than the viscous scale. In basically what can happen is that the burning front can burn through a region faster than an instability can grow. And sometimes we call this the fire polishing scale, or can burn through the smallest eddies and set a lowest scale in terms of the length scale of turbulent eddies that can actually affect the burning, which in turbulent combustion is usually called the Gibson scale. On the same token, the turbulence affects how the burning takes place. When you have turbulent convection, it can mix fresh fuel into a burning zone and help reactions really go nonlinear or help prompt thermonuclear runaways. And again, as Bob showed, turbulence can wrinkle a flame and can accelerate the flame's speed directly. So having these two, the two physics, having the hydrodynamics and combustion, when you're modeling them together and ensuring that you're doing it accurately, takes some care. Just here's some examples. This is from a long time ago, something I did, I guess, even when I was a postdoc. This is looking at a Rayleigh-Taylor unstable flame. So this is, I forget which is which. I think this is carbon fuel, and this is ash carbon burning into magnesium, I think in this case. This is a high density, and this is a low density. And you see as the density decreases, at high density, the burning happens fast enough that it burns through the smallest wavelengths of the Rayleigh-Taylor instability before they can grow. And it makes a nice, sharp, well-defined flame. But at the lower density, the Rayleigh-Taylor can grow faster than the burning takes place, and it creates this very convoluted, wrinkled flame entering the regime of what we call distributed burning. So this is an example of how the turbulence can and the burning can interact. Whoops. Sorry, hit the wrong key. Another example is in classical novae. Classical novae are when you have an accreted hydrogen-helium layer or solar composition layer on the surface of a white dwarf. And the burning is taking place in the hydrogen layer, usually by CNO, then hot CNO. And CNO burning is catalyzed by carbon, nitrogen, oxygen. This is hence the name. And so when you have just this solar abundance hydrogen layer above a carbon oxygen white dwarf, if you have a lot of mixing at the interface, it can drag catalysts. It can drag carbon and oxygen into that burning zone and greatly accelerate the thermonuclear runaway of the nova explosion. In fact, as far as we understand, you need quite a bit of mixing in order to get something that looks like observations. And so this makes modeling classical novae very challenging because you really got to do a good job with that mixing. So here's some computational challenges. So those are two astrophysical examples of where burning and reactions interact. And here's some computational challenges. If you want to model turbulence and you're doing pure hydro, we all know that you just want to use a lot of resolution and or a high order method so that you can really separate the scale of where you're depositing the energy from the dissipation. You can get a nice turbulent cascade, and you can see this well-developed turbulence. When you're doing multi-physics, though, and you have other things besides hydrodynamics, resolution isn't the only thing that you need to optimize. So, for instance, one of the problems that arises when you're modeling explosive reacting flows or very vigorous reactive flows is that you can dump the energy into your system on a time scale that's comparable to the hydrodynamics time scale. And it can cause you, when you're doing the reactions, it can cause you to wander away from what the true solution is of a coupled hydrodynamics reacting system. And one of the ways that codes often get around this is they cut the time step. If you reduce the time step to be well below the hydrodynamics, the Courant limited time step, then you do a better job at coupling the reactions in hydrodynamics, and you're evaluating the reactions at a more accurate thermodynamic state as you're doing your evolution. The problem is that hydrodynamics methods, the way that we develop them, the numerical viscosity tends to scale as 1 minus the Courant number. And so if you drop your time step greatly, you're increasing your numerical dissipation. And so this is, you did all this work to do very high resolution, but now by dropping the time step just to get better reactive coupling, you're going to introduce more dissipation, and you're going to change how well you're actually resolving the turbulence. Another way this also comes into play when we're doing modeling is sometimes when you're doing reactive hydrodynamics, a simplified equation system is used during the reactions that can drop the overall convergence of your scheme to first order. Again, undoing the hard work you've done in preparing your hydrodynamic system to be high order, and you're losing accuracy because of how you're choosing to solve the coupled system. But we can develop methods that can do a good job on this, and this is what our group has been working on for the past few years. A long time ago, we worked on the first part is getting around that Courant limit, and the way we did this is by developing low Mach number methods that can model stratified flows. And this is an image from a simulation done back in that time of burning inside a white dwarf. So again, very akin to what Bob was showing, but this is earlier in the stage than what Bob did. This is showing contours of energy generation in the center of a white dwarf, and the red and blue are showing outflow and inflow of these convective plumes that have developed inside of the star. And by developing a new algorithm that can move along at the hydrodynamic speed instead of the sound speed, we're able to evolve this system for much longer, but also take a time step that is more natural to the time scale at which the turbulence is developing. And this helps again, with reducing the numerical dissipation. If we did this with a compressible code, we'd have to take several orders of magnitude more time steps, each adding to the numerical diffusion, and it would affect the development of the turbulence. To get around this problem of having to cut the time step in order to accurately evolve a reactive flow system, we've been developing new time integration techniques that strongly couple hydrodynamics and reactions. What's often done in reactive flows, especially in astrophysics, is an operator split method, where you burn for half a time step, advect for a full time step, then burn for the second half of time step. And if you do this correctly, and I will note that a lot of times it's not done perfectly correctly, you can be second order accurate in time. But when you're reacting, you don't know that there's advection going on. And when you're advecting, you don't know there's reaction going on. And so as a result, if you dump a lot of energy into a zone, the flow doesn't respond instantaneously to help quench that burning as it's happening. Instead, you're lagged because of your operator split method. Realistically, the burning should respond to the flow. And we've developed some methods, starting with a spectral deferred corrections method back in 2019 that can couple hydro reactions to fully fourth order in space and time. And then we've come up with a simplified method, because that method was complicated, more recently, that strongly couples reactions and hydrodynamics. And when we're reacting, we're actually solving an evolution equation where the reactions see the advection. There's a little bit more expense, at least on paper, in that we have to do it twice. We have a predictor-corrector formalism. But the fact that you include advection while you're doing the reactive system means that you actually help alleviate some of the stiffness from the reaction integration, and then the computational work can actually be less than doing the operator split method. The upshot of this is that when we model problems like detonations in a supernova, or the problem I'm going to show now, convective burning and mixing in a massive star, we can evolve the reactive system along at the Courant time, and we remain strongly coupled. And we don't have to artificially reduce the time step in order to get our code to behave well. Because when we're reacting, the flow is responding directly. And when there's a strong hydrodynamics flow, the reactions are seeing that. And so our burn is seeing what's happening in the hydro as it's happening. We implement this in our code Castro. It's open source up here on GitHub. It runs on CPUs and GPUs. Most recently, we've been running a lot on AMD GPUs. And it has several different methods for doing the time integration. The traditional operator split method, the second and fourth order true spectral deferred corrections methods, where you basically pick some quadrature method and iterate until you converge to that quadrature over some time nodes, and this simplified method that is sort of the best of both worlds. So I'll show you a problem here, and I'm trying to keep track of time here, of modeling a massive star. And the challenge with a massive star is it's big, and the textbook definition is that, textbook picture is that you have lots of concentric shells of burning. You have an iron core surrounded by silicon shell that's burning, surrounded by oxygen, neon, carbon, and so forth. Each of those shells is dumping ash on the shell beneath it. They're all convecting, and at the interface of those, there can be mixing. The 1D picture of this nice concentric burning shells is probably not borne out in reality, and so we'd like to understand how this plays out in a massive star. So we've been developing a way. I'll get to that in a second. This is an initial model. Got to move this zoom thing. All right. This is what our initial model looks like. This is a log scale. You have density in blue, temperature in orange, and the electron fraction in green. The vertical line here, this is how big our domain is. So we model basically capturing the all the way to the helium shell. And this dotted line is where our highest resolution is. Everything inside of that we model at a high resolution. So here's the iron core, here's the silicon shell, here's the oxygen shell, here's the carbon burning shell outside of it. And the star runs out, it's about 5 to 6 times bigger than the sun in this case. This is a 15 solar mass star. So we've developed this, our spectral deferred corrections method to work with nuclear statistical equilibrium, which is what happens when in the core of the star, when you're at temperatures of several billion Kelvin, that photons have the same energy as the binding energy per nucleon, and you can actually undo all the work you've done in fusing light elements to heavy elements by photons breaking them apart. You build an equilibrium where the reverse and forward rates come into a balance, much like a chemical equilibrium. And the star will want to stay at this, except inside the massive star, there's a lot of weak reactions. Electron captures, beta decays, and the positron equivalents taking place that's driving the evolution, and in fact, further driving down the electron fraction, ultimately leading to the collapse of the star. So what we do is we build a big table of NSE. We're doing this with an open source library that we developed called PyNuke Astro that captures the correct composition as well as the evolution of the electron fraction due to weak interactions, and it allows us to blend nuclear statistical equilibrium from hundreds of nuclei, or order 100 nuclei, to an on-grid network of 19 nuclei and seamlessly blend these together. And in particular, we've developed the algorithms such that we capture the NSE evolution to be second-order accurate in time. And so over the time step, because the flow is evolving and the temperature is changing and the density is dropping and YE is evolving, we're actually evolving the NSE state in our coupled reactive hydrodynamics update as the system evolves. A big difference between what we're doing now and what has been done in the past is we can do all this on the CFL timescale. We don't have to artificially drop the time step by orders of magnitude in order to remain well coupled. The fully coupled nature of this spectral deferred corrections method ensures that the two processes remain coupled. That means that in terms of turbulent mixing, that we would have less numerical dissipation because the dissipation scales as 1 minus the Brownian. These simulations actually run pretty fast on 32 GPUs. We can use maybe 1,500 node hours, not that much, and run for 5 or so minutes. And we get something that looks like this. Here's the massive star. This is showing only the inner 1% of the simulation. The blips at the beginning were our way of initializing a self-consistent convection. Here's the core, iron core. Here's the silicon burning shell outside of it. Here's the oxygen burning shell, at least part of it. The domain extends quite a bit further. The electron fraction, I don't have it here, but this is the mean molecular weight. The electron fraction is evolving in the core. You see that there's a lot of shear at the boundaries between the silicon burning shell and the oxygen burning shell. The silicon burning shell in particular looks rather ratty here. And eventually, at least in this calculation, some blob of fluid gets in and the whole thing collapses. All right, so the main moral of my story is that in contrast to hydrodynamics, where to capture turbulence well, you really just want to drive to high resolution or use a high order method. When you're doing multiphysics, you have to worry about the coupling, because if you do a bad job at that, you can introduce more dissipation than you might expect, especially if you drop the first order because of how you decided to couple things together. And so we've been working on methods that allow us to strongly couple hydrodynamics and reactions. I showed you the application to a massive star, but we've applied this to X-ray bursts and Type 1a supernova as well. And I think I'm out of time, at least according to my clock. So I'll stop there.
Hi, I come from the combustion community, so for me, as far as I'm concerned, the split time scales are the de facto, the routine. It's been a long time around, but when you mean diffusion, you mean mass diffusion? Is that what you mean?
In astrophysics in general, mass diffusion is not important.
So what do you mean by diffusion?
Radiation diffusion.
Radiative diffusion, okay.
Yeah.
All right. So I would say that your time scale should be, for the reaction that is, should be the smallest of, maybe below that of hydrodynamic, radiative diffusion, etc., right? To let all other processes being able to do their job before you do the reaction, right?
The reactive time scale is small. In astrophysics, the nuclear reactions, they tend to be more stiff than the chemical reactions. And like is done in chemical combustion, we use implicit method subcycle to make up to the hydrodynamics timescale. But the point is that as you're evolving that reactive system, so one thing to keep in mind, some of our reaction rates, so for like helium burning, it scales as temperature to the 40th power. So you want to know how the thermodynamic state is evolving as you're doing that reaction over delta T, because it's an enormous change in energy, especially if some flow's going on that's expansive and is going to cause the burning to quench a bit. And so this coupled scheme, what it does is when it's doing that subcycling of integrating the reactions to make up that the delta T of your global time step, it sees what the advection is doing. So there's an explicit advection term, and so it'll respond to that as it's evolving.
Now, this is precisely what I was saying, that it's more than just the hydrodynamic time that you have to take into account. You have to take into account all other processes.
Absolutely, yeah.
Except for the reaction to have your split time, right?
Yes.
Okay, so we agree on that.
Last quick question, anyone? No? All right. Thanks, Michael.
Thank you.